Well, we're not to quantum mechanics yet. This is a doorway to it. I brought in Schrodinger's cat just for the sake of the humor of the how they behave. I will now put the Schrodinger cat to bed here and play this. The idea of today's lecture is to give you a feeling and a quantitative understanding of what is the single most important effect in all of physics, and will continue to be so for the time that I can see in the future. And the start of this really comes with the laser revolution. But this particular fellow here, Ken Evenson, was responsible for increasing the accuracy or precision of the speed of light by 3 figures. That brought it up 10 figures. And he then hectored the international metrology community to take the speed of light that he had measured and define the meter by it. And once we did that, what I call the precision revolution began. If it hadn't been done, we wouldn't have a GPS system. So this is really the beginning of having that kind of precision, where you can have a satellite up there that locates you. Well, the standard ones you get at Walmart locates you a few meters on the surface of the globe. You can do better than that. You can actually locate yourself in just centimeters. So this is an amazing thing that's happened here at the National Bureau of Standards, is what it was called then. It's now the National Institute of Standards and Technology. Ken died of Lou Gehrig's disease long before he should have died naturally. So it's with sadness that I talk about this, but it's an incredible achievement that he made. I'll talk more about what he actually did later on. But I would like to, this is, I say, anonymous, but I'll let you guess who said it. Without resonance, we as humans, blind, deaf, and dumb. With our eyes, there's an incredible resonance going on in the chromophores each time you see a color or something moving. Ears definitely need resonance. No way you're going to hear anything. Signals are so weak from the sound. Okay? And talking, that's resonance. It's a little more crude than hearing, but it still doesn't happen very well without resonance. So the thing we're going to learn about today, and it's mostly a review, the sophomore physics, well, you could say that it was Riemann's equation, which we're skipping for the time being, as I mentioned in an email I sent out. But what I would like to do is take this apart here. This is just a plain old mass times acceleration equal force, F equal ma, Newton 2 here. And we're going to take it apart right away, just with respect to handling a simple oscillator. And for our purposes right now, it can just be a mass on a spring, which we'll simulate, but obviously it will have this one run just to give you an idea about all of the constants and figures of merit that engineers and scientists of all kinds use when dealing with resonance. So we'll start off easy. Just to start off with a thing that we kind of have been doing all along here in this class with the phasers. And we mentioned that early on in the business. And then once I get a few things straightened out about this, we can go on. But I want to make very clear that the complex wave function, but here oscillator variable, a phasor clock that turns clockwise has to, that's a velocity. I say here if the is where the oscillator is, and then where it's going to be that's velocity, that's the imaginary part. And the imaginary part is just the velocity scaled by omega. Scale in any other thing and you get an ellipse for an oscillator, but we pick a circle, and I've talked about this a little bit already. We use these phasors to do the coupled oscillator, and we'll come back to that in the lecture on Wednesday. But in any case, the thing that I have here is the simplest possible, as far as the numbers go, oscillator, and that's a 1 Hertz oscillator. Heinrich Hertz is the guy that brought us a radio that you could actually talk over. He didn't live very long, about 35 years. And we'll see him again when we talk about per time, per space wave vectors. That's Heinrich Kaiser. These two guys were born within a few years of each other. Heinrich Kaiser has his name on wave vector, and it's why we have a wave vector K, as far as I can tell. Anyway, this is the thing which I will start a simulation of, just to get the numbers started here. This is a 1 Hertz oscillator. That's a 6.2832 radians per second. And as you can see by the plot, it's going through the integers every other swing. That is, there it goes through 3, then comes back down through 3.5, and then it goes up through 4. So this is a 1 Hertz oscillator. And we'll be playing with all of the constants that go with this, including force and stimulus and all that. And those numbers will be on the upper left-hand corner of the simulations that we do. So that's our animal. We're going to treat this animal, all the things that can happen to it. We're going to turn on the friction, which is missing right now, and then we're going to attach to the right-hand side of this equation a stimulus, which resonates, and that's the real resonance mechanics there. So in any case, I think that's all we have to say. Now you notice that I've got the real part of the phasor in this direction. Obviously, it would probably be better, and we'll certainly do this for waves, is to turn the whole phasor up so that it matches the amplitude of the actual oscillating body. Okay, let me pause this and go to the next step here. I'm going to go ahead and take it back to the lecture part. And these are, of course, simulations that are clickable from anything that you can get off the web from our site. So the next stop here is to see what friction does. We haven't talked much about the friction in mechanics. Most of mechanics deals with the pure thing. It doesn't have any of that. But here, friction, even a tiny amount, has a tremendous effect in some ways, and then doesn't have any effect when you consider other things. So that's something we got to get used to. And will be the sort of a battle between the friction, which is indicated here by a damping constant. The coefficient of the velocity is 2 times the constant that is conventional for describing oscillators. So that gamma there is a coefficient that uses that notation very often, especially in quantum mechanics, but in classical considerations it has a merit of long time use. In any case, with this damping force and the little extra term here, we have a trick which we kind of use this trick to do the cyclotron orbits. That is, use complex variables. Don't bother with the old ways of handling the differential equation like that. This one is perfect since it's homogeneous in coordinates and derivatives. Just simply set this oscillator variable to a e to the minus I omega t, minus I because phasors go clockwise, and the minus I omega squared there becomes this after I've taken a minus from across the whole thing here and divided out the omega. So we now have an equation here for the actual frequency of this thing. This is the natural frequency of 1 hertz. This is going to change it just a little bit, just a little teeny bit, and that's really important. So let's go ahead on both of these and see how that works out. With that equation being solved, we get two frequencies, an omega plus and an omega minus. And that could mean that we'd like to keep track of the frequency for something that's going counterclockwise. But we have everything going clockwise here, so we don't need the other sign. We just keep the plus sign for that right there. And all of the oscillators that we will work with here will have a minus icon, so minus I on the gamma, so it'll be a minus gamma here, and that will factor out as a something that controls the amplitude. So there'll be a big effect of this friction on the amplitude, but not such a big effect on the frequency. The frequency will be reduced, but it's being reduced in a Pythagorean way, and so that constant that we call omega gamma here, it's not too different from omega 0 for the cases that I'm taking here. And the cases that I'm taking here, as I say, are only reducing the frequency very slightly. And this is an important number here, how much does it reduce it? But the basic idea is you have a Pythagorean difference here, and just expanding that shows you right away what the situation is. You have here gamma squared. And we have for this, this particular case, and let's go ahead to where we can actually see it. Let me go ahead and run a simulation for this case right here. Again, a 1 hertz oscillator now reduced a lot in amplitude, but I don't see much reduction in frequency. It went right through the 1. It's going to come back and go right through the 2. So to within a width of the line, we're seeing no effect on the frequency, but we're seeing a considerable effect. With this particular gamma, that's 0.2, a gamma of 1/5, versus an oscillator of 1.0. So the idea is that we're pretty close to 1.0 hertz, pretty close to 6.28, that's 2 pi frequency, omega frequency, the one that has the 2 pi attached to it, which is the most common place to put it in almost all of physics and engineering too now. So as you can see, we're already down to 8 seconds on the simulation there, and it still doesn't look like there's much of a change, and that change of course is in the 4th decimal place. So you're not going to see it for a while. But that exponential has had a big effect. And the question is, how do you think about that exponential? How do you quantify it? How do you give a figure of merit for the oscillator based on that a constant relative to the frequency here, which is just 1 hertz? So that's the next step here, really, for this, is to make that case. Now, here is the trick that I have used all the times I've been dealing with oscillation, both in quantum and classical. And that is that the e to the minus 0.05, that's 5% minus, that's pretty close to what we've got here, is well, let's just show it here. E to the minus 3 is 5%, to 3 figures. Okay? So what we're looking at here is to figure out how long it takes for this oscillator to reduce by 95%. That is, to be reduced, and it's now off the screen there, but at about 15 seconds, and that's what you get here by going 3 over gamma, and gamma is 0.2, that's what we have, and we've got the minus 3 here on the exponent. that means that at 15 seconds, we are down to 95%. So rather than use the standard 0.69 half-life of an oscillator, let's do the 95% life instead of the 50% life. And obviously 50% life is very common in study of radiation decay, but for this decay, I really would like to use this. This is you'll see other reasons for doing that as we go along here. So, here at 15 seconds, which is right about there, this thing is 5% of the amplitude it started. Now, it's kind of interesting, the amplitude that it started with, I started with a velocity and not a position. All of these curves here have a beautiful geometry of tangency just off of the center of each of the oscillations. And that's a little bit of geometry that's kind of neat about the exponential. Okay, let's go back now to lecture both of these. Move these other guys along so we keep track of what we're doing here. And the next step here is to really get the figures of merit in our minds. Now, if you really want to be precise about this damping effect, I recommend e to the minus pi. And this is interesting in quantum mechanics when you're matching wave functions at a boundary. This is very close to this, but using this, e to the minus pi, and it's an easy number to remember, 0.04321. So 4 figures there gives you e to the minus pi, okay? And then we get a time for that number. Instead of the time for 5%, I'm going to be 4.321% reduced in my amplitude, and that will be 15.71 seconds instead of 15 seconds, okay? So that just gives you a feeling of how the arithmetic goes if you take advantage of this. So this is the time required to reduce the amplitude to 5% of what you started with, or, being precise, 4.32% of what you started with. Okay. So this is a major trick that I like to, a numerical trick that I like to extol the virtues of. Now, on your lecture, you will have the ability to click back and forth, at least I hope you will have that ability at this moment right here, where this is going. This figure of merit that we're getting here, that is the number of oscillations that you get, or the time that you get, lifetime that you get with this reduction by either 5% or 4.32%. This 15 seconds that you get is given by, and that's just the arithmetic of this, very nearly equal to, if I set 3 equal to pi, cancel them out, I get this omega sub gamma. That's the new frequency that we have, is slightly reduced, divided by 2 gamma is giving us the major effect here, which is your 95% loss. Basically, we're giving a lifetime that I think a stock broker or banker would say, if you've lost 95% of your capital, you're dead. Okay. So the dead oscillator for us is, well, this is even worse, 15.7 seconds it takes with the fancy exponent of pi. Okay, so this lets you go and see where this is headed. I'm going to click ahead here to here. We're going to be talking about how all the properties of a driven oscillator and a resonance, okay? And there's a number there that describes that we call the Q factor. And it happens to be omega, not omega gamma, but omega 0, but over 2 gamma. Omega over 2 gamma is what I call the angular quality factor of this oscillator. Okay, so that is going to be an important thing. And then you jump ahead to page 42, which will be there shortly enough, but you can see The standard quality factor is just 2 pi scaling of ours that we use, okay? So let's go back to page 18. And you can go back and forth between these as we discuss these quality factors that really give you a way to very quickly, shall we say, quantify what's going on with any kind of resonance, optical, mechanical, or whatever. And here's where that begins. Now we're going to have everything going. We're going to have a stimulus force applied by an electric field on the outside. We're going to scale out the E over M ratio that we talked about in the last lecture, and that will be our force. Acceleration is what we're talking about up here. And that's the force divided by the mass. And here are all of the characters of this play are now going to be in effect. And in general, the electric field will be any function of time, but you can guess that we're going to be making that be an oscillation as well for the first go-around here. In any case, what we're about to do here is calculate the Green's function for this equation. That's what we need to find out. In other words, we need to find out what is the response with all this stuff going at once. And that is indeed very important. So we're going to be solving for the z value. That's the actual coordinate of motion here, the real part of the phasor. And we're going to be given a certain amplitude for the stimulus. And this equation describes that. But here's what the equation actually looks like when you put it there. And the solution, well, it's kind of weird, but let's do something that's pretty crazy. Let's just divide by the operator. We're talking about the inverse of the operator, aren't we? Should be able to take that, especially for a situation that has an exponential function that is a complex, imaginary exponential function describing the stimulus, the accelerative stimulus. This is acceleration, A, little a, that we're talking about. That's force divided by m. Okay, so just keep that all in mind. We're being very careful with units, unlike most of the days in this room. So anyway, this 1 over the derivatives, double derivative, just becomes minus omega stimulus squared. Single derivative gives you an I times 2 gamma, single power of omega s, and then of course we've got the natural frequency, our 1 hertz frequency right there. So putting those all in place with the real part first and the imaginary part second gives you what will essentially be our Green's function for this. This is what we're going to be applying to the inhomogeneous part of the differential equation. That's what's going to happen here. We're just going to multiply by the Green's operator, it's complex operator, so that's a fair name for it. And they have the acceleration right there. That's going to give us the stimulus amplitude. Okay, well, it's going to do it with a little bit of labor. We've got a couple of things to do here. But anyway, that's the way I like to write it. And there's the guy that's responsible for doing this probably the first time. This is a long time ago. Mr. George Green. He was born on almost my birthday, but I was a little late than 1793. This is a long time ago. Okay, it's a pretty long time ago. I'm not that old, but he is. And it's also another guy involved in this as well. This whole thing, this Green's function, is really called the Lorentz-Green's function. And we're going to be seeing the Lorentz resonance curves in all their glory today here. In any case, there it is, and there's Heinrich Lorentz Now he comes along a little bit later. This is 1853. He's 1793 birthday. Okay. He is honored in Cambridge with a plaque, which is not too well cared for, as you can see. There's a lot of dirt on it. But anyway, what are you going to do when you're a physicist? Anyway, the idea is to separate this thing into real and imaginary parts. And we did a little complex analysis, enough where you should remember that you simply multiply and divide by the conjugate of whatever is in the denominator, and that will clear the denominator of imaginary quantities. So that's all there is to this particular Green's function. We're done once we've done that. Okay, so we're going to have a real part of the Green's function, that's this guy, and an imaginary part. And we're also going to have a polar form. This is real and imaginary, so that's Cartesian view of the Green's function. We still have to do the polar part. Okay, so that's a little bit more complicated, but still, all this stuff is really quite simple. And we're interested in a very important angle. This is going to be our phase lag angle. Because after all, we've got a phasor associated with this quantity here. This is what our Green's function is going to give us. It's the actual amplitude if you put in the phase factor, or keep the real and imaginary parts in track. It's two basic variables in either case. Okay? So here's a way to view this thing that I think is convenient, is we've got this phasor going around, but the response, that is, if the stimulus is here and it's going around driving this thing, there's a block diagram that you might draw for this, some electrical engineering problem, okay, and there's a response coming out of, and there's the stimulus going in, and then the Green's function's converting that to a response. The response is going to be at some angle, namely this angle right here, to the stimulus. And most of the time it's going to be lagging behind it. So we generally call that a response, a phase lag. But it can get ahead, and we'll talk about that too. So it could be on either side of that. But when rho is positive, we're talking about dragging behind. Okay, so these things are going around at the frequency of the driver. Okay, that's this omega stimulus. Okay, and it can be any value, but we're interested in when that value is pretty close to the natural frequency, omega 0. And what's amazing about this is that we're not so interested in omega gamma. It isn't much different from omega 0 for high quality oscillators, as we've seen, but still exactly omega 0 is what we key off of in the stimulus business. Okay, so let's see if there's anything that's being left off here, just to point out where rho is in the equations, and as a lag of something going clockwise. We're all talking about left-handed phasor motion in this business that uses the complex way of looking at it. So we do have a real axis and an imaginary angle. We'll see that in great detail shortly here. Okay, so let's get all of that up here. And here's the picture that's on the cover of this unit 4, and it is got some interesting geometry associated with it. But let's say what it is that we're going to be keying on, what's going to be interesting. We're going to be interested in, first of all, where you get a peak of the real part, or the imaginary part, or the actual amplitude. Okay? The amplitude is indicated by a yellow curve, which is hiding behind the blue curve, making a sort of greenish there. Then the real part peels off as we go to higher frequencies. Now we're in the resonance region, which is from here to the other side. And at that point, the real part of this Green's function takes a nosedive, goes right through omega 0. And then goes to some values approximately the same as this, but not quite, and then finally comes back. And on this side of the thing, you get all kinds of weird wave phenomena when you're looking at the resonance in a wavy system, where the speed of the wave is considerably larger than the speed of light. Whereas in this region, on this side, it's what you're used to, is that a wave going slower than the speed of light. This is called the refraction function, or the diffraction function. Refraction, better name. And then this right here, the imaginary part of the Green's function, that's responsible for the loss. And that's the absorption part. It's probably a good name for it. Okay, so this function has a nice app that goes with it, but since it isn't moving, I don't need to really show you. You can play with it yourself and see all the different shapes you get. But what we're most interested in as far as coherent optics or whatever, spectroscopy, is the phase lag angle. And that's what this is. And it's falling pretty close to a circle. Do you notice the circle has a little flat tire there? That's the DC response, which is this height right here. How much of a resonance do you get at 0 hertz? Okay, you get no resonance. You get no help. So let's make that more vividly true by taking this. It used to be a 1 hertz oscillator, but I lost the other masses, so it's a little faster than that. But let's just talk about what the DC response of this is. I come in with my electric field. It's really weak electric field. I mean, you know, it's just a feather, right? It's a broken feather. I mean, how can you do anything worse than that? All right. So here I go. I'm going to try to raise this thing without any frequency at all. That's as high as I can get. But if I do this, if I get in phase with it, actually pi over 2 out of phase, come on, baby. I got to get in tune with it. But if I can keep in tune, if I can keep the phase, baby, I did this real well when there wasn't anybody watching, but I'll see if I can. You sort of have to watch it there. So here's the name of the game. Each time I come in with the right phase, I add the DC response, exactly that much. And we'll see that in the simulations. Okay? Now this is a pretty high Q oscillator. It's a lot better than the one we've got. And we'll estimate that later on. But this is what we're dealing with, and let's go ahead. And this is an ugly picture from my early days with the old, you know, the early Macs. They could draw things with pixels that were, you know, about as big as postage stamps. But it's enough that you can see the picture. This is a new thing that TC has given with HTML5. But in any case, here's all the stuff. Real part, imaginary part. And this is interesting. What we're interested in is the ratio of the response at resonance. And I mean right when omega 0 is being the stimulus frequency. Not omega gamma. I don't care about omega gamma. All I care about is omega 0. And that's what's in the equations, you see. Omega 0 is separate from omega s, so you don't worry about it when you're doing linear resonance. Okay? In any case, the ratio of this function, g, it consists of this collection of variables for the real part and the imaginary part. Now, when omega 0 is omega s, this is gone. There's no real part. That's the real part that took a nosedive right here. You can see that more clearly on this particular chart right here. That comes right through there at pi. Okay? So, that's the basic idea of this. Actually, it's 2 pi that it comes through right there, 6.28, and that's that's because this has killed it. The stuff in denominator will come. But this one right here, when omega s becomes omega 0. Okay, well this disappears, but this stays. This second term here stays, okay? And it's squared with gamma, so it's going to end up with a gamma in the denominator. Okay? And the omega s is squared. So the stimulus frequency right here, this guy, let's see if I got that right. I've got 2 gamma s here, and then I've got 2 gamma s omega s. So I end up with basically the frequency omega 0 over 2 gamma. Okay. Right there, this 2 gamma cancels 2 gamma squared. Okay. That is what I was mentioning before, angular quality factor, right there. Omega 0 over 2 gamma. Before, we were worried about the omega gamma, omega sub gamma over thing. We do not worry about that. But just to check that, I'm going back to page 18 here real quick. There's omega gamma over 2 gamma right there. And then I'll just come ahead here to page 35, where we are right now. Okay? So there's a really important number there. The resonance response over, that's this, over this one. Okay? Well, that's coming out to about 15, which is how many wiggles it took to kill this thing by 95%, to kill the resonance by 95%. And it makes sense, because this is a 1 Hertz oscillator, and every Hertz I took 1/15th off of the amplitude. So this is a number of heartbeats in the lifetime of the oscillator. And to make this human important, ask yourself, how many heartbeats do you get? If you're healthy and you live a long time, you're easily going to get 2 billion. If you're not so careful, it might be a little less than that. Okay? So that's your Q factor, 2 billion, if you were talking about an oscillator, okay, in its lifetime. Right? It's good to put numbers on these things and talk about crazy things that are related to. It gets you, so you really begin to understand quantitatively what we're dealing with here.
Question. Why is it called angular?
Well, I put the name angular on this guy, okay?
Yeah, why?
Because he's dealing with radians. Okay, that's angular. This is angular frequency, which has the angular frequency is 2 pi times what other people would call the Hertzian frequency, right? Cycles per second.
Yes.
This is 6.28 times that. This gives you the angular. Okay, so this little q, I'm putting it as a little q, but a little bit later, you see, we're going to talk about big Q, okay? That involves frequency, not omega. I just put a little nu there. Omega 0 divided by 2 pi, okay? Our angular thing divided by 2 pi is what everyone else calls the standard Q factor. Okay? Does that answer your question?
Yes.
So don't mix those up because they're different by 2 pi. Very common error, and almost, I think I can name 3 times when I listened to a lecture where some guy had left out the 2 pi. That's a big deal. That's 6.28. You left that out, huh? And you're doing precision spectroscopy? Not good. Okay, so you got to watch out for that, right? Well, let's go back to page 35, which is where we're just now getting this stuff lined up here. Okay. So as we see later, the capital Q factor is what most people talk about, but you can see how useful the little q is. Counting heartbeats, right? Giving you ratio of this to this. This here times 15 gives me this on resonance, all right? and then other times not so much. And as the quality of oscillator gets big, this gets tall. Okay, just increasing my or decreasing my gamma factor, the resistance factor, by half, bring it down from 0.2 to 0.1. Whoa, I can't plot the thing here. It's already on the second floor, right? So this is a pretty impressive skyscraper. This is about what they're building in New York City right now, literally. They put a base that big and they build a tower about that high. It's crazy. I don't know if you've been to New York or looked at a picture of New York, but there are all these needles going up there. And then in Dubai, they're out doing that even. So these buildings, these resonant things get really tall. How tall? For a typical light like in that projector right there. I'm not talking even lasers, which are really coherent, really incredible cues. The cue up there, it's on the order of 50,000. Okay, we're talking about just, a little bit of an amplification here. That's 50,000. That's typical quantum cues. Incredible amplification that you get with high quality resonators. Okay. All right. Now, we've taken care of just 1/2 of the response. At least when you're starting this thing up cold. You apply the stimulus at a dead oscillator. That's what we'll do in our simulations. It has to build up. You can't just go right to the resonant value. It takes a certain number of oscillations to get there. And the road isn't easy because there's lots of damping going on with the gamma. At least, well, not lots, because we have a pretty high quality oscillator, but this is a very 0.2 gamma is really stinks in the laser business. I think I have a better situation right here because this thing has gone way over 15 oscillations, right? This is a pretty high quality oscillator. Okay? It's in hundreds. All right. So, we need to figure out this thing right here, known as the homogeneous solution. This is what you get with no stimulus force. Okay? What does it do for you? It allows you to set the initial values or boundary conditions. Sound familiar from your electromagnetism when you're doing Green's functions there? Right? You have a Green's function. First of all, it'll tell you what happens to the field if I've got some charges or charge density, right? But then you got to set the boundary conditions. So you got to add to it a certain amount of the Laplacian solutions, the solutions with no charge, right? Well, that's exactly what we're doing here. This is the inhomogeneous solution that only responds, it only marches to the stimulus. It doesn't give a damn about the boundary conditions. Okay? And this is what you're going to get after you've waited a long time so that this dies. This is going to die. So if you're a long distance from the charges, well, okay, that's all you're going to, you're not going to see this anymore in this particular application. Okay? So this one is not a function of initial values. It's added to something that is totally a function of the initial values. I have to tell you exactly what this is, and it's complex, so this is in general a complex number. Okay, so that's the part that we have to do now to get this a complete story. Okay. The other names for this homogeneous solution, it's known as a transient solution. Since it dies off as the exponential here, which has a big effect, goes forth. And that one is a function of omega gamma. But this one here just marches to omega s and has a phase lag that's constant. So this is called the steady state solution, since it's present long as the stimulus is operating. And is the whole story very soon, about 15 seconds in our simulations. This is not playing much of a role because it's down to 95% ND and dropping fast. Okay, so that's the thing that I want to talk about as we go through simulations. Okay, so I'm going to advance this screen here to the point where we can play the various issue. Now, I think that'd be a good thing to start off with way below resonance simulation. Okay, so, and this is straight out of the textbook, so you can see these numbers being shown next to figures that look like that. And I'm going to go use this guy down here to take us to that resonance. Okay, so here's the stimulus now. There's the response right there. You can see it's right behind the force by some angle, which you calculate here. It's 0.14 radians behind it when we're in steady state. But it's catching up, and it passes. It's like a car passing a snowplow. As soon as it passes a snowplow, it realizes it's in deep snow and starts to slow down and finally drag behind the force. Okay? So now the Z, the response, is behind the stimulus. Okay? Not by much, but when it settles down, and we're less than halfway, well, about halfway there now to the 95% point, at about halfway, we're going to settle in on only 0.14 radians behind. See, I tried to pass a snowplow again. I'm using winter analogies. Most of you people don't know what I'm talking about. If you live in the East, you drive to work each day, and the snowplows are there, and if you're in a hurry, you try to pass them. Big mistake. Anyway, we're getting there. We're down to 11, now 12 seconds. We only got 3 more seconds to go here with this 1 Hertz oscillator. And already you can see the beating between the frequency of the stimulus and the natural frequency is settling down to the stimulus frequency. It's settling down to this all by itself. This is dying. The transient is transient. That means it doesn't last very long. But you can see the beats that you get on the way to being in a steady state. Almost 100% now, within a couple of percent of being 100%. We're settling down on a single amplitude right here, a single phase lag right here, and that's the natural situation for a driven oscillator. And this one is well below the resonance, so you don't have much of an amplitude. You have a lot more than the DC response. The DC response is about 3/4 of that. But aside from that, it's Dullsville from now on. You're just going to have the oscillation that's associated with this frequency and with this amplitude. That's dead. Does that make sense? Okay? That's the day in the life of a low-quality oscillator. Okay? Well, it's not so low quality. 0.2 is pretty good for a mechanical system. All right? Now let's go to the other extreme. Let's try for this one. So I'll just go ahead here and actually kill it. Actually, I should just simply pause it so I won't use up CPU time. Going and doing this again here by clicking on this guy here, on resonance. Okay? Now, we are running the stimulus at the frequency this device wants to go. 1 Hertz. We're running the resonance at 1 Hertz. So it matches omega 0. Not omega gamma, but omega gamma is different from omega 0. So we don't really even have to mention that. But anyway, what we're getting is an Archimedean spiral right here. Not a logarithmic spiral, but an Archimedean one, whose amplitude at first is going up by the same amount each pulse. But out here now the friction is getting pretty high, so we're not gaining as much as we're used to gaining. And you can see that by the amplitude of the response. The response is curved, was starting out on a straight line, but now it's curving out and reaching, and here we're approaching halfway to the 95%. We're going to be seeing that as pretty close to the what you're going to get forever and ever. That is what you're going to get for this term by itself.
Excuse me.
Yes?
What are those two envelope lines in middle?
Oh, that's just showing what would be the oscillator that was pulled to this particular DC response and let go.
But the
That would just be the
initial
oscillator itself.
amplitude is even different than that.
That's the one that would go down to 95% there, right? That's what it would look like. I just put it in there just as an indicator of what's happening to this. You see, as I get down here, the transient is 5% of what it was here.
Mm-hmm.
And it's a really tiny percentage of what the oscillator's now doing. But the timing is what I was interested in. It's just to see, there's 5% right there for just the oscillator let go by itself. Okay? The same constant is affecting this whole term here, because when this guy's off, this guy gets to be maximum. That's the resonance amplitude that you're going to be seeing from now on. If you can see this thing, it trails off about there. No beats, just one big beat if you're on resonance, because there's no difference between the stimulus frequency and the natural frequency. There's no beating going on. You just do beat, and at the magic time of 15 seconds, the lifetime, we say 95% lifetime, right? You're pretty close to maximum. You're within 5% of as big as it's going to get. And then another 15 seconds, you're 5% of 5%. You can't tell the difference from the steady state all by itself and having a little bit of this left. You always have a little bit of this left because it's exponential, right? Yeah.
Can you get the Q from the plot?
The Q, you mean omega, that's omega over 2 gamma,
Yeah.
okay? Omega 0, all right? 6.28 over 2 gamma, okay? Over 0.4. That's your amplification factor. Omega 0
I mean,
over 2 gamma.
From this picture with the blue and red.
Well, we could if it's about that big, right? You can see how big it is. It's from there to there, right? And that's pretty close to it, right there. And what we worked out before for that amplitude, that's what this guy is right here. Because he's taking the, he's multiplying this guy. Green's function is multiplying whatever the stimulus is. So what you're talking about is the ratio of this guy to your response.
Yes. But it doesn't look at 50.
Say that again.
That red?
Yeah, this has been always the same amplitude,
Yeah.
okay? And that has been working on this system, and let's take this one back.
But
Just a
here
C.
the Q should be 15, huh? Or am I wrong?
This is the resonance response, okay? And this is the DC response. So this numerator here is this, okay? And the denominator right here, that's this. So the omega 0 over 2 gamma is giving you a ratio of this to that. Okay? Whatever you would have gotten in response from running this stimulus at 0 frequency, ratioed with, that's this number, ratioed underneath what you get here for the value of stimulus equal natural. Resonance. Perfect resonance. Okay? That ratio is 15 here. For the reason that I mentioned when I did the feather thing, right? I go, each time I did a jump by that much. That's the DC response, low frequency response. Okay? I don't get much. It never grows. But if I have the frequency of my feather going at exactly the resonance frequency, which is hard to do, it's a high quality oscillator, and I'm pretty clumsy at it, right? But if it's a perfect one, right, here, I would be getting every time the same rise. Every time I would be getting that much. Then I get it again. Then I get it again, but a little less because now the friction's going up, right? And then I get even less here and even less here. But if I had no negligible frequency, this spiral would keep going. We'll do that in a minute. Okay, that's when you don't have any friction at all. Or you have a high quality oscillator like what we have in quantum mechanics. Does that answer at all what you're getting at?
Yeah, thank you.
Just think of it as I do this much, then I do this much, and then I do this much, and I do that 15 times, I get to what this is approaching at long time. Okay, let's kill this one, and I'll bring us back here to look at some extreme cases. Okay, extreme case when you're talking about, and I've got to jump this thing ahead to about there. Now, if you're way above resonance, I'd like to talk about that, but that's a whole nother thing. This is the, on resonance simulation that we just looked at, and this is way below resonance. Now, you probably noticed, if you looked at this carefully, you've noticed that this one ends up with the steady state in the same, just a little bit behind the stimulus. This one, the response, here's the stimulus, here's the response. The response is 90 degrees behind this as it goes left-handed, okay? This one is 90 degrees. This one is even more. This is more like almost 180 degrees behind. That one is a real killer, and that it might not hurt just to go ahead and do that. Let me see. Let me remind myself of where we're going here. So on resonance, I went backwards. Did I go backwards there? There we go. Okay. Here's gamma nearly equal to 0. Okay. And here's what would happen with that situation. Always the same amount, you see. Not like that thing where it finally dies and reaches a steady state. This is a long way from steady state, and if it has no friction at all, if you're doing a superconductor or something like that, this goes forever. Okay, this straight line just goes forever. Unlike the one that we were looking at before, where it reaches the maximum. Okay, so that's lots of friction this is no friction, practically no friction, okay? I have to say nearly equal to 0, because if I set it equal to 0, the program will explode. You'll be hit by computer shrapnel. Okay, not really. Anyway, that's what I would. Now, we can take a little bit of a time here. I think we've got another 15 minutes or so here to play with this. These are things that you should play with, just to get a feeling for it. This is with practically no gamma at all. Okay, I've got the gamma 4 decimal places, 0. Okay, I've already got a huge phase lag, and I'm talking about a frequency that's a little bit faster than the stimulus. So this guy's racing out there and going to pass the stimulus. Now the response, that's this guy, is passing the force, passing the phaser, okay? But as soon as he passes, oh gosh, his phase is not favorable for gaining. So a beat occurs. He starts to say, oh gosh, I shouldn't have done that. I shouldn't have passed the snow plow. And I run into all the snow. I'm slowing down. Bad analogy, but it's a way to remember it if you've lived in the East. And look at that. He goes to 0, comes through, and goes right back out, because we have some numbers that are within ratios of each other, and goes right back out and retraces this whole thing. So this thing is going to have a beat, and then it's going to have another one just like it. It's really cool. See, the phase is perfectly matched. We're doing the same thing over again. So this is an example of being off resonance, and it'll just beat. There's no friction to speak of, so it's going to take up and do this forever. All right? Okay. I killed something there in the process of going up there. Let me pause this. Bring this one back home to where it was, and let's go and do maybe on this one. I'll advance this one a little bit, and we'll take this one is where we still have a gamma of 0.2, but I want to look at what you get when you're above resonance. Okay, so this is really high frequency compared to what the oscillator wants to do. It can hardly, you know, pretty soon it's completely out of phase with the thing. Very close to being completely out of phase. Now it's 180 out of phase. Now it's even more than 180 going behind the thing. Right? And you see the beat coming back. And in the process, once it does that, it's giving energy back to the field. The field's a huge field though, so it doesn't change amplitude. Next lecture, we're going to talk about when these two can change amplitude. Only this one can change amplitude. And I come out on the other side there with a mini beat. Not as big as this one, because remember, at 15 we're going to be down 95% with this thing, and we'll be reaching a steady state, which will be a much smaller amplitude. And that's the thing that's true about these curves, these response curves. And I'm going to back up here just to make sure we see that response curve again. This one. Here we've got a DC response. We don't have high frequency response. At high frequency, this goes force power to 0. That's really important. That's really important to Röntgen, who discovered that you could make light go through almost anything except a heavy metal. This is how X-rays work. The frequency is too much. There's nothing there to respond. The electrons, they can't possibly respond to that. Now the nuclei, they still can respond a little bit. And when that happens, of course, you start to do nuclear physics. That takes gamma radiation usually. Very few transitions in X-ray for nuclei. Okay? But in chemicals, they respond quite a bit to ultraviolet and then X-rays, okay? But at high frequencies like that, most things just sit there and they're out of phase. Basically, the force going this way when the force zigs, this zags. And the force is here, it's just back and forth like that. Doop, 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 doop. Okay? You're at steady state. This thing's probably way down on the second screen, right? The rho is now 2.9, almost 3, almost pi, almost 180 out. And we're not very high, very far above resonance here. The frequency of the stimulus right here is 7.5. The natural frequency is 6.28. It's only, you know, one hertz or so above a natural frequency. And already we're seeing X-ray effect. This light would just pass through anything that is resonating, not resonating. Okay, it has a transient and that's it. And it's very small. So that now we're over here on this diagram.
Excuse me.
That diagram we need to understand. Yeah.
Oh, I think I missed this definition. How do you define something if it is on resonance above or below it?
Oh, okay. Just by being, if you're above, you're higher with the stimulus than the omega zero. When you're below resonance, your stimulus is below omega zero. Or zero. That's as far below as you can get.
It's not based on the Q you define it?
Well, the Q is just giving you amplitude information. What you're talking about is
Yeah,
phase
yeah, yeah.
information, okay? And that's interesting. Right here, you see they're in phase, pretty much.
Mm-hmm.
That's DC response. Okay, you go this way, you tug it over, right? You go back, it goes with you, right? So that's what you have right there and nearby. It's practically a straight line right there. Okay. But as I get out here, I start to see resonance beginnings. Now I'm still below resonance. I'm still much less than resonance. But I'm getting there. I'm getting there, you see. And then there's kind of the magic. This is halfway up the peak. It's called full width half maximum. That's the full width. Half width is to the midpoint. That would be HWHM. These are things that you should get used to because you're going to see them in the literature. People that work with this stuff all their life will say, "What's the matter with you, stupid? Don't you know what that means?" You can get up on it right away by these particular pictures. But anyway, to answer your question, here's below resonance and there's at resonance.
Yeah.
And then
But
there's
based
above.
on the other slide, you show.
Let me go.
No.
Go this way, this way, this way,
No,
this way, this
the
way.
one that had 3.
Okay, let's keep going. Head
No.
here. We'll go ahead
Go
here.
ahead, right.
To these guys. Okay, this is
Yes.
way above resonance,
Mhm.
X-ray-like stuff.
Uh-huh.
There's on resonance. Now they're equal. And then here's way below. That's when you're doing the just plain DC following. See, there's no phase lag, practically. Here there's 90-degree phase lag, and here it's almost 180. So there are the three extremes. This is the one that you're most interested in because it's going to have the most effect. This is the least effect, pretty much, but this is really the least. This is what goes to zero response when you go really fast. You're too fast for it. So it's just going to zzz like that while your force is doing this. It's just going zzz, 180 degrees out of phase.
Mhm.
The phase lag is like when you apply electric field and then the amount of time that the electron is getting affected by the electric field, right? That's the phase lag.
At this point, where we're going for a long time, the phase lag is constant now. It is right on 296, right on 296, 97. So it's right on 3. Okay, and that will not change. They are rigidly locked. Those two. What does that mean? When this one is down, that's up. When this one is up, that's down. Okay, that's 180 out of phase. That's what it means. Practically 180. Does that answer what you're asking? Yeah. Whereas all of these others, this one is way above, just like that. This one, when you're 90 degrees out, wow, okay? That's when you get the resonance. Let's see why that is, okay? What's going on here? This arrow, the force, is pulling on that thing. Think of that arrow as pulling on that Z there, okay? Think of trebuchet motion we talked about, okay? You get in phase with that thing, and you get to give it energy. Now the force is in sync with the velocity. Okay, the velocity is maximum there, and the force is helping it along. It says, come on, baby. Come on, baby. Force down there. Come on, baby. Force up here. You're making F dot V maximum. Force lined up. And as you can see, growing in amplitude as a resonance because of that. The only thing that's keeping it from going forever is the friction. We've got a lot of friction because we've got a high gamma, 0.2 now. But that's the way it's going to be forever, 90 degrees. 1.57 is rho. That's pi over 2. That's 90 degrees. Pretty close. Look at it from the point of view of here. This one gets up high. Let's see if I see when the amplitude is high, the velocity is 90 degrees. You see, when the amplitude, that's the blue thing, that's maximum. It was way up there, now things going back down. But what you want to look at is the force being 90 degrees out with the coordinate means that it's in phase with the velocity. When that thing's coming up, the force is working on it. Working on it. It's pushing it up. Now it's pushing it down. Now it's pushing it up. So you've got F times V maximized. Force times velocity is power, right? Is this making sense? Is that what? Single most important effect in all of physics. But there's another kind of resonance. It's nonlinear resonance, and we'll get to that. It's called parametric resonance. It's a whole other story. But this is what usually happens day to day. That other stuff, it's dangerous. Okay. Now the thing that we have not yet, and we're right now at a time if we come on time, so 5 more minutes, I want to take from you right now. Because this is an important part of our physics is approximations. How do you approximate all this intricate algebra that Green has given us? How do you handle that? And quite apart from, here's a review of the Q factors, what I call the heartbeat count, and all of those numbers. Those are worth nothing. And then what's your amplitude doing? E to the gamma t squared, that's e to the minus 2 gamma times time. Okay, that's where the Q factor. It's just the same thing with a 2 pi on it. But here's where we do an approximation. Here's where we turn the classical Green's function into a quantum propagator. That's the name it's given. It's a little weird. But what I do here is I imagine that that omega s, okay, as I let omega s, the stimulus, approach resonance, every oscillator looks a little bit like a high quality one. And if I can set omega s in all of these equations, at least into one of them, if I can go ahead here and factor out an omega s and pretend that omega 0 and this, see, I can take this omega s and bring it outside of this. In fact, I'm going to take 2 omega s out of there, and I can write this whole thing as this, just 1 over omega 0 minus omega s. If I can get away with that, if I can write this, I've got a really simple Green's function. I've got a detuning, and I've got a drag or friction or decay. I've got detuning and decay, 2 DEs. Those are the factors. So at this point, I get what most people call the Lorentzian, this thing. It's a constant over a variable plus the constant squared. Okay, so this is an approximation for the Lorentzian. This is what most people call the real Lorentzian, this thing. And then that's the imaginary part. Here's the real part. That's the one that gives you the up and down thing. This one gives you the lump. The witch's hat. Remember the witch of Agnesi? That's it. Okay, so I want to real quick go through that because we've already done the complex analysis of this. This is a good way to write the Green's function magnitude times e to the I rho is cosine plus I sine rho with that amplitude. There's the magnitude of the Lorentzian. That's the function right there. It's the square root of a sum of squares. We've seen this before. These are the Smith plots. There's a circle here and there's a circle there. It's the orthogonal bispherical coordinates. And here's the Thales geometrical construction of the circle. Okay, this is a right angle sitting in there. There's a rectangle sitting in there. We've seen that before in a number of problems that we've done in this class. Okay, so it's worthwhile seeing. This is the ideal Lorentz-Green's function, if you will. It's the one that's going to play a role in quantum mechanics because quantum mechanics equations are first order. This is a Newton's equation, an oscillator equation, is second order. Much more complicated. This is that thing. And then here are the circles that TC has given a whole bunch of things that you can draw here. This is just what we've seen already in the complex variable analysis. There she is, beautiful Maria Gardina Agnesi, Italy. What a being. Okay, and here's her hat that she is named after, the witch's hat. Okay, you've seen that, right? Well, what's missing is the real part. Okay, this is the imaginary part. This is the real part. Common Lorentzian function of the refractory structure. That's what gives you your speed of light on one side faster than speed of wave on one side faster than light, slower on the other side, on the low side. Okay. So I just want you to be aware of this geometry. You can do this with a ruler. This is what you can do with a ruler and compass. I also want you to be aware of the opposite extreme, really terrible oscillator. 0.2, that's pretty good. But let's see what one would do with 2. That's something you should play with. This is kind of really grungy oscillators you're going to get in some of the solid state of physics. Here are the flat tire. The DC response is as big as the resonance response. There's the DC response. It makes a huge flat tire. It looks like a snail. It's sort of hanging over the positive side there. And here's that dip curve. This beautiful thing here has just become almost, if you put any more gamma on this thing, this becomes flat. It just sort of curves over and goes down. Extreme friction. is that one, okay? We've talked about the circles, right, that give this. We've talked about this 3D picture, right? There's the refractory, there's which effect Nisi going the other way, cutting through this 1 over z squared potential, okay, which we looked at. All right, well, that's about it. We're now on time for the class since we started 5 minutes late. And we will take up the next thing, which is 2 oscillators fighting with each other. That's a different kind of resonance. But it's based on this one. Okay.